structures. Today's focus is going to be on alkali aggregate reactivity in existing concrete structure. It is certainly a big challenge for engineers to determine what are the best things to do on concrete structures affected by ASR, and the management of aging concrete structures is certainly a huge challenge. In order to do that, the most common steps to be used by engineers and practitioners is to determine what is or are the cause of deterioration and how severe those deterioration are. As you can see in this picture, this bridge has been demolished about 2 years ago and was quite badly affected by ASR. You can see the different symptoms of deterioration, cracking in different parts of the structure. And the structure was also quite heavily affected by the effect of freezing and thawing actions and corrosion of reinforcing steel. Determining the cause of concrete deterioration and the mechanisms involved is not necessarily easy to do. An example can be given here, like those railway ties in northeastern USA. Those ties have been affected by ASR and other mechanisms of deterioration. As you can see in this slide, the signs of DEF, delayed Ettringite formation, can be seen here by the presence of Ettringite forming, deposits at the periphery or surrounding the coarse aggregate material in the concrete. And there has been also at the same time obvious signs of ASR present in the ties in the concrete. ASR gel was found in the aggregate particle as well as in the cement paste, indicating that both mechanisms were present in the concrete. So what was the exact cause of the first mechanism who started the process was a debate among experts, and it's, as I said, it's not always easy to determine which is the main cause of the problem. Also, it is quite critical to determine how severe is the deterioration going to be, and at what rate is that deterioration going to develop. So you can see in this pavement here, you have some cracking happening in the different sections of the pavement, and with time, as the deterioration will continue to occur, you will see spall developing at the joints here between the different sections of the pavement. So those spalling are such critical that they need to be patched, as you can see here, and at some point the pavement will need probably to be overlaid, or something very, very important will need to be done with it, like a replacement or some other actions. It is also quite critical when, especially in northern states or countries where ASR develops, but is not only the action going on or the mechanism involved. Like in this case here, you can see cases of ASR and freezing and thawing that are affecting some concrete elements, and with time ASR is obviously increasing the internal deterioration in the concrete element, but freezing and thawing action is certainly a major factor contributing to the distress, at least at the surface layer of the affected concrete element. So as part of the Federal Highway Alkali Silica Reactivity Development and Deployment Program, a number of tools were developed for the management of aging concrete structures. And you can see those 3 of those documents on the screen right now. By the way, those 3 documents can be downloaded from Federal Highway website. If you type ASR in the search mode, you should be able to find those documents. So the first document is called a report on the diagnosis, prognosis, and mitigation of ASR in transportation structures. So this document is a fairly extensive and detailed document that covers those three major topics for the evaluation and mitigation of ASR in structures. The second document is called Alkali Silica Reactivity Surveying and Tracking Guidelines. This document is meant for inspectors and those who are managing concrete structures over time, and it provides a number of suggestions and guidelines for evaluating the presence and the extent of ASR in different type of transportation structures. And the third one, the Alkali Silica Reactivity Field Identification Handbook, is actually a document that the inspectors can take with them in the field in order to help identifying the presence and the extent of ASR in concrete structures. So let's have a look at those documents in more details. So the first one is called the Protocol B, or Report on the Diagnosis, Prognosis, and Mitigation of ASR in Concrete Structures. You see the table of content on the screen right now. Basically, as I mentioned earlier, that document, that report, actually provides a number of information, test methods, and recommendations for the diagnosis and prognosis of ASR. So all different approaches in order to cover those different topics related to ASR, as well as there is a chapter on mitigation measures. So in other words, when you have identified the presence of ASR in the structure, what are the most likely solutions in order to take care of this problem in your structure. And in appendices of this document, there are a number of test methods that are proposed actually in the process of diagnosing and doing the prognosis of ASR. So those test methods are given in very much details, and a lot of information is provided to the potential users. So in this report, there's also a flow chart like that is a logical way of identifying the management approach for ASR in concrete structure. So in this flow chart, you can see that there are two major sections. One deals with diagnosis, and the second one deals with prognosis. So really, the logical pattern to evaluate ASR in concrete structures starts with the inspection by the field inspectors in order to identify ASR in concrete structure, and then based on the visual survey, a probability of the presence of ASR or alkali carbonate reaction, ACR, can be identified right there. If there's a potential for ASR or ACI to be present in the structure, there's a recommendation to take some samples from some cores from the structure in order to confirm the presence of ASR or ACI in the structure. And when the presence of ASR has been confirmed, then there are also suggestions on an approach for the prognosis of ASR. So it means how fast is it going to develop in the structure, at what rate is it going to develop, and this can be done through in situ monitoring approach and also advanced laboratory investigations. So the second document I mentioned, the Alkali Silica Reactivity Surveying and Tracking Guidelines, is basically a document that will help the inspectors for inventorying, surveying, and tracking ASR in the transportation structure. And the main focus in this document is on bridges, pavements, and tunnels. So basically, this document provides a basis for identifying and quantifying the defects that are potentially caused by ASR. So it means that we review the different types of features of deterioration that can be identified by inspectors in the field with a special focus on ASR. And all this documentation that can be generated through field inspection is intended to serve as input to management systems used for bridges, pavements, and tunnels. As a support for the surveying guidelines document, the third document, which is the Field Identification Handbook, is really meant for inspectors and consultants who actually will carry out the field investigation, the field survey, in order to identify the presence and extent of ASR in structures. And it complements the first document that I mentioned, the report for the diagnosis, prognosis, and mitigation of ASR in structures. And it refers also to this handbook for the identification of ASR in structures, which has been developed in the past, in the early 1990s, by Dave Stark and his group under the SHARP program. This slide actually gives some details on the table of contents of this Field Identification Handbook. So as you can see there is a lot of information that is provided in this document related to the actual field symptoms of ASR. So what are the different field symptoms that the inspectors can identify during their work in the field. Also, we spent some time giving some information about the effect of exposure conditions, for instance, moisture and temperature on ASR. And the second part of the document is actually presenting a lot of examples of ASR, either by itself or in combination with other deterioration processes such as steel corrosion, freeze-thaw action, delayed detrangite formation. So a large number of pictures are given with descriptions of those pictures for ASR in bridge structures, pavements, and other transportation structures. Again, as I mentioned, in order to help the inspectors in their field survey to identify the presence of ASR and the extent of deterioration due to that deterioration. So if we look at the first at the bridge inspection, there is the AAR guide manual for bridge element that was introduced in 2011, and this AAR guide is commonly being used and can be used as the basis for the element visual evaluation. So it means that in that document, a lot of information is given to inspectors on how to evaluate the presence of different features of deterioration in bridges, and the identification of those features of deterioration is well explained in that document. But what we are providing in addition to this guide, AAR guide manual with the tool that we're proposing is really to identify defects that are kind of specific or unique enough so there would be a possibility for the inspector to have a feeling of whether or not ASR is present in the element that is inspected. So those defects that are particularly related to ASR, that are not necessarily specific to ASR, but that are present when ASR is affecting concrete structures, those elements that are being flagged by the inspector will be mat cracking, align cracking, gel exudation, and relative dislocation and misalignment. So we suggest as part of the process, as in the AAR document, for inspectors to evaluate the condition state of the different bridge elements according to this first table, condition state 1 to 4 being from good to severe. And then also to track the environmental conditions to which each element of the bridge are subjected to. This is very, very critical, as you can see on this picture, where you have a beam here. A part of that beam is under the deck and shows very, very little cracking compared to that section of the beam that is exposed to moisture and show extensive cracking due to ASR. So that's why for the inspectors it's very, very critical not only to identify the presence of those features of deterioration, but also the effect of the moisture condition on the development of those features of deterioration. The ASR surveying and tracking guidelines also include a number of tables that can be used by the inspector in order to have a better idea on how to quantify those condition states, how to determine which condition state we are for each of the different elements of the bridge, according to those features of deterioration that have been flagged since they are most likely present when ASR is affecting bridges. Not always, not to large extent. It will depend obviously on the extent of ASR in the structure, but those are the different defects that need to be evaluated, and those are the different features that can help the inspector to classify the different elements in different condition states. And another table here is more precise as the compared to the previous one, where basically for each of the different features of deterioration, specific information is given to the inspector to classify the condition in state 1, state 2, or state 3 according to the crack width present in the element, the area affected in the element, and also in terms of gel exudation, what is the area affected by the gel exudation, and for the relative movement, because ASR is not happening at the same extent and same rate in the different elements of the bridge. So that's why there could be some movements between bridge elements. So depending on the extent of the movement, then the condition state can be classified from 1 to 3 according to this table. And as part of the tool that is the ASR Field Identification Handbook, pictures are given, as you can see here on this slide, of the different states, condition state of the different parts of the bridges. Like here in bridge deck, we have examples of minor cracking, moderate cracking in bridge deck. There are pictures also showing moderate cracking and severe cracking in bridge abutment walls. So those pictures will definitely contribute to the determination of the condition state of the different elements of the bridges. Other examples of different features of deterioration, as you can see here, that are ranging from moderate to severe in different bridge elements, and beams like that, in the base foundations of columns, and reinforced concrete columns as well. So all those pictures are provided in the handbook and will help the inspectors to classify the condition of the bridge elements. So at the difference of the bridge structure, there are no standard or national approach to inspect concrete pavements. A number of those approaches are actually have been developed by states or provinces or countries. So there is no real national standard for pavements in terms of evaluation. But what we suggest in our ASR surveying and tracking guidelines is actually to use the same approach as what we propose for bridge structures, is that to determine a number of features of deterioration that can be associated to ASR. So according to this document here, is the Federal Highway Administration Handbook in 2003 for pavements. This document lists the defects in jointed concrete pavement and in continuously reinforced concrete pavements. So those are the different defects that the inspector will be looking for when they want to evaluate the condition of a concrete pavement. So in our ASR surveying and tracking guideline, what we suggest to do is for the inspector to focus especially on those different features here, problems at joints, map cracking, pop-outs, map cracking as you can see here, in the different pavement sections, as those features of deterioration could actually be considered as potentially indicative of the presence of ASR in the concrete pavement. So the guidelines, once again, provide tables like that that will help the engineers and the inspector to for the interpretation of those different defects that will be affecting the concrete pavements in order to classify the deterioration that is observed as condition state 1, condition state 2, or 3. And based on that, the different elements of the pavement will be classified. Once again, the ASR Field Identification Handbook provides a number of pictures to help the inspector to do the evaluation in the field, as you can see in this picture. Once the field inspection has been completed, and in some cases some concrete structures may have been flagged as potentially affected by ASR, another step in the process of determining if ASR is really present or not is to go and try to find the documentation associated to the structure evaluated. So all that documentation is not necessarily available to for the inspector, but here you can find a list of the different documents that could be used, that could be very useful to help the inspector for the interpretation of the field observation. For instance, documents that could be very interesting would be the type and location of the structure, the likely exposure conditions. This is very critical since ASR will likely develop faster in those parts of the structure that are exposed to moisture. The age of the structure, details and dates of any modifications and repairs. That's also quite important to know. If there are any plans, drawings, and specification available to determine what was the drawings or the condition of the structure. Then if there are any details on the concrete mixtures that were used, especially the mixed proportion, whether there was any supplementary cementing materials used in the concrete. If there's been any previous inspection or testing report, especially information dealing with deterioration, if it was observed and when, and also information from other structures in the area that may have been constructed with similar material, and if there is any deterioration in those other structures, that could be information very useful for interpretation. So going back to our flowchart, now that the routine inspection has been done, the question that is up to the inspector and the engineers: what is the probability of ASR in that structure, in the pavement or the bridge? So obviously, all the information that was obtained from the routine inspection is going to be used for establishing that probability. If the probability is none or very low that ASR or ACR is present in the structure, then the option at that stage would be to simply go back a couple of years after the first inspection to determine whether there has been any further development of deterioration, and then track the progress of those symptoms of deterioration that were associated to ASR. But if the probability of ASR or ACR is medium to high, the next step is to go ahead with sampling of the concrete structure. So the sampling is done for diagnosis. So it means that cores will be taken in order to determine whether ASR is present and could be a factor responsible for deterioration. So cores will be taken in bridge elements or pavements showing signs that are suggestive of ASR, as you can see in this example here, gel exudation or efflorescence, as well as cracking. And then cores could also be taken from less deteriorated or less exposed components of the structure in order to compare the internal sign of deterioration, if any, and then that could help in determining whether or not ASR or ACR is present in the concrete. Petrographic examination is really the main tool here that will be used to determine if ASR is present. The evaluation of the cores can be done right after extraction of the cores, or when the cores are brought to the lab not too long ago after the cores have been taken. And already a fair number of information can be obtained from the macroscopic evaluation of the cores, like the presence of cracking, the presence of exudation or efflorescence at the surface, some gel in air void or air pockets at the surface of the cores. So all of those elements can already be determined right after taking the cores out of the bridge element or the pavement. So the macroscopic description of the cores can be done, just hold on a second, I'm going just to try to, okay, no. Sorry, I'm just trying to get rid of something on my screen. Okay, I think that's, okay. So sorry for that. During the macroscopic description of the cores, as mentioned earlier, features of deterioration will be noted, such as the presence of the macro crack at the surface of the element, the presence of exudation of gel or efflorescence at the surface. Also, when you look with the geologist's lens, you can see the cracks, and sometimes the crack will go through aggregate particle, and already you can see the presence of alkali silica gel in the aggregate particle right there. So those are elements that can be noted right away at the examination of the cores before doing any cutting or slicing or breaking of the cores. The cracking pattern is really something that has been proposed in the past and is still very, very interesting in order to determine the presence of ASR or other mechanisms of deterioration in the concrete. This sketches of patterns of cracking have been proposed by the British Cement Association Diagnosis of ASR Handbook back in 1992. And in that document, you can see a number of those sketches that are presenting different types of deterioration in concrete, not only ASR, but also freezing and thawing, delayed etrangite formation, and other mechanisms. So the use of polished sections that are obtained from cores extracted from the structure will actually provide an opportunity to evaluate the cracking pattern, as you can see here. So quite typically, when ASR is present in the coarse aggregate particle, there would be a specific pattern of cracking that can be observed. So you have macro crack present at the surface of the concrete element. Those macro cracks are generally related to differences in the moisture condition between the surface or the skin of the concrete and the internal portion of the concrete, where micro cracks will be more developed than at the surface of the affected concrete. So this pattern of cracking is quite typical, and in the internal portion of the concrete affected by ASR in coarse aggregate, you will see the cracks actually running through the aggregate particles and from one aggregate particle to another through the cement paste. As you can see here in this real example, you see cracks due to ASR running from one aggregate particle to another through the cement paste, and alkali silica reaction product can be seen both in the aggregate particle as well as in voids of the cement paste. Another example here involving a very highly reactive chert particle, you can see once again the cracking running through the aggregate particle as well as in the cement paste, and you can see the reaction products present in the cracks in the cement paste. When ASR has been developed through a reaction with the fine aggregate fraction or the sand fraction. The surface section of the concrete will be pretty much the same, where macro cracks will be observed. In the internal portion of the concrete, though, the cracking will actually develop further in the cement paste, running from one aggregate particle to another, but running through fine aggregate particles, as you can see here. This is the sand. Those are the reactive sand particle, and the coarse aggregates in this example are not reactive at all. It's really the fine aggregate, the charred particle, that are reactive, and you can see the cracks running through the aggregate particle and the presence of alkali silica gel in the cracks. So obviously the secondary product that from ASR, what we call the alkali silica gel, is a main feature that petrographers will be looking for to confirm the presence of ASR in the concrete. As you can see here, you have gel in the cement paste, in cracks of the cement paste, gel in voids of the cement paste, and also gel in cracks of the aggregate particle. As you can see here, when the expansion and the ASR is generated in the coarse aggregate particle, and here in the sand fraction. The presence of alkali silica gel is not necessarily easy to determine. Sometimes the amount of gel also present in the concrete, despite the fact that there is a fair amount of cracking, the amount of gel is not necessarily that important. So in the late 1980s, early 1990s, there's been tools developed in order to help petrographers to determine the presence of alkali silica gel, and it is related to the use of the urinal acetate staining. So this is a solution that can be applied on the polished surface of a concrete like that is affected or not by ASR. Here you see the reaction products in the cement paste here. And when you apply this urinal acetate solution at the surface of the affected concrete, there will be an ion exchange process between the alkalis present in the gel and the urinal acetate from the solution. And this ion exchange will contribute at doping, if you like, the gel with that urinal acetate ion. And when you expose the treated concrete to ultraviolet light, the gel actually will become much easier to identify, because it's going to glow in under the UV light. So that's one of the tools that has been developed and proposed. Unfortunately, a number of states do not allow the use of this technique because of some environmental issues. It's slightly radioactive. This tool has been and is still being used in some cases. Could be quite useful, but the use of it will be really a function of environmental issues in the different states or location where you need to apply it. So you can see here the presence of alkali silica reaction product in voids of the cement paste. As you can see here, also in cracked surface of the cement paste. This is on broken concrete surfaces. Alkali silica gel is, as I said, a main feature of ASR, obviously, and the identification of that secondary product is quite critical to the confirmation of ASR in the concrete. The gel staining using the urinal acetate solution can be used also on cracked concrete surface. The example I gave before was on polished section. It can be used also on cracked concrete surfaces, as you can see here. And after the exposure of the cracked surface to the urinal acetate solution and under UV light, you can see that the gel is actually glowing very well under UV light. And this is a concrete that is affected by ASR, and this concrete has no ASR, so you don't see the same type of feature after the application of the urinal acetate solution. In view of the limitations in the use of the urinal acetate solution. A group from Los Alamos Research Station has developed another staining method using sodium cobalty nitrite solution that can be similarly to the urinal acetate solution that can be actually applied at the surface of a broken concrete core or a polished section. And the application of that solution through a chemical exchange process, again, between the solution and the gel, will contribute at staining the gel in yellow, as you can see here, which can help in determining the extent of ASR affected parts of the concrete by the presence of ASR gel, as you can see there. Another very important tool that can be used by petrographer is the use of thin sections. So thin sections will be cut from the concrete core. So the thin sections are very, very thin plate of the concrete, about 30 micrometer in thickness. And the thin section is placed on the plate here of a petrographic microscope. There's a source of light at the bottom part of the microscope that go through the concrete section, and then the petrographer can look at the section through the light actually going for the light going through the thin section, as you can see here. So this is the view that the petrographer will have of a concrete here affected by ASR, where ASR is present in the sand fraction. The coarse fraction of the concrete is a limestone, a non-reactive limestone in this case, and the sand fraction includes chert that is reactive, and you can see here cracks in the chert particle that run from this reactive particle through the cement paste, and the gel, the alkali silica gel, is going to be found also in the air void of the cement paste. So the use of thin section evaluation like that can be a very powerful tool to identify the site of expansive reaction as this reactive sand particle in the concrete. In order to confirm the nature of the reaction products, the alkali silica gel can be actually evaluated also using the scanning electron microscopy. This is a piece of concrete affected by ASR. You can see cracks here that are filled with alkali silica gel. So the scanning electron microscope will not only be a tool to confirm the presence of the gel, but it can also confirm the composition of the gel, which has been in many publications highlighted as a feature of ASR. So the composition of the gel is very, very specific, and the use of scanning electron microscopy with a tool for chemical analysis can be very critical for that. Here you can see some pictures, micrographs that were taken from under the scanning electron microscope. The alkali silica reaction product that you can find on the cracked surface of the aggregate particle most of the time will correspond to crystalline product of ASR. And then when you reach the limit of the aggregate particle going through the cement paste, you will see a more massive type of gel that present at that location that correspond to a layer of gel on the surface of the reactive particle, as you can see here. When the gel goes through the cement paste, its composition will change. In the previous slide, we saw that the composition of the gel when it is inside the aggregate particle is normally richer in silica compared to calcium. When the gel reaches the cement paste, actually the composition will change, and the gel will actually contain more calcium than silica, and then the gel will be more massive in microtexture, as you can see here on the cracked surface of the cement paste, and in air voids also you can see the massive gel lining the air void. So those are typical features of ASR that can be confirmed with the scanning electron microscope, where you can see the microtexture characteristic of the gel as well as the chemical composition to confirm that ASR is really the factor responsible for the cracking. This report here, one of the tools that I mentioned earlier, this document is actually providing also for the petrographer a number of tools for the interpretation of the petrographic examination. So we are including in that report a number of tables like that will classify the probability of ASR as low, as moderate, or high, as a function of the different features of deterioration that are being obtained by the petrographer. So I will not go through those in details. I'm just mentioning that because you can find this information in the report, and this is very interesting supporting information to help the petrographer for the interpretation of the petrographic examination. So after the petrographic examination in the laboratory, the next question will be to determine whether ASR obviously is present or not. Through petrographic examination, if it has been determined that there are no signs of ASR in the concrete, but still the concrete is in relatively bad shape, then there might be an opportunity to investigate for other mechanism. But if ASR is present, then engineers will determine at that stage whether or not it is required to do some further testing, evaluation, or if mitigation or remedial action can be taken right away. If there is no need for further evaluation through detailed program, then sometimes immediate remedial action can be taken, and this will be discussed further by Professor Flowchart in the next presentation. If there is no need for immediate action, then there's a possibility that the deterioration is considered not severe enough to do anything at this stage. So the next step will be to go back to evaluate the structure in a couple of years from now to determine the progress of the deterioration. But if there is a need to do some further testing, evaluation, because the concrete structure is a fairly large structure and the engineers might need more information about the extent of ASR in the concrete, then there's a possibility of doing a detailed evaluation program to evaluate the prognosis, so the potential for future expansion, either by in situ monitoring or advanced laboratory investigation. So in situ monitoring will be one of the interesting steps. For example, one approach that we're suggesting to do is to determine what we call the cracking index. So when you have an ASR affected concrete element like this one, there is a possibility of drawing at the surface of this element. This is a Jersey barrier in this case. Drawing a sort of a cage at the surface of the element. The distance between the marker here is about 20 inches, and the approach that is suggested is to determine the cracking index by counting the number of cracks that are met by the different lines of this pattern here. And not only counting the cracks, but evaluating also crack width along those lines. So this process is called the cracking index. So if you count the number of cracks and the crack width, using a table like that, you will actually multiply the number of cracks by the crack width to determine the amount of cracking in terms of millimeter per meter of lines on the concrete, and then this information can be used to determine the condition of the concrete. So with time, if you run that cracking index every second year, for instance, you can determine whether the cracking index is increasing with time. This is going to give you an idea of of whether or not ASR is actually progressing inside the concrete. This slide is just giving you an example of the use of this cracking index procedure. This is on another project where those concrete elements have been extracted from housing foundations, and there is a process of deterioration in the housing foundation that is also related to aggregate expansion. And so the lady here is actually measuring the expansion and the cracking index on this face of the concrete wall. And as you can see here, for this plot, you have expansion as a function, the percentage of expansion as a function of time for over a 1-year period using this measuring device here. You can see that during the 1-year period of testing, the expansion is actually increasing, and at the same time you see also that the cracking index is increasing similarly to expansion. So this confirms that the determination of cracking index could be a very useful tool to evaluate the progress of expansion in concrete structure affected by different mechanisms. In this case, it's another type of aggregate-related problem. Expansion or deformation measurement also can be used. What we have been using and we're suggesting is you can use the same pattern that you use for the cracking index to measure expansion. So this is about 20-inch in dimension. And you can see here Dr. Thomas actually drilling in a concrete pavement section in order to insert a stainless steel pin that will be used to measure expansion, as you can see here in the pavement, using that measuring device. So that process can be used in pavement, in columns, as you can see, jersey barrier walls. So and the idea is to monitor the expansion over time from year to year, every second year if you like, in order to have actual measurements of the progress of expansion in the concrete. One example of this process being used is a bridge structure in Alabama. It's the Bibb Graves Bridge in Wetumpka, Alabama. Our team has been involved in the evaluation of one arch of that bridge that is very badly cracked, as you can see here. So we have been installing on the, you can see here a polished section from that arch element that shows a very extensive cracking due to ASR, and there are a mixture of alkali silicate gel and secondary yttrangite that in the concrete. And we've been measuring expansion in different portions of this structure, and we have found over a 4-year period that the expansion was about 0.12%, which corresponds to about 250 microstrain per year, which is considered as a high rate of residual expansion or progressive expansion. So the monitoring of expansion can provide useful information to evaluate the progress and the future potential for expansion. Since ASR is also very much related, obviously, to temperature, and the extent, I would say, of ASR very much related to the temperature and the humidity, one approach that is interesting, especially when you, and Professor Folliard will talk about that in the next presentation, when there's a plan to actually evaluate the effect of surface treatments on ASR-affected structure. It is quite interesting to actually measure the internal temperature and humidity in the concrete. So there are different tools that can be used for that, electronic probes like that, or a wooden stick like this technique that has been developed over the year, where either a probe or a wooden stick can be inserted in the concrete, and with time measurements are being taken with specific tools like this in order to evaluate the progress of humidity reduction, if you like, in concrete that has been treated with surface treatments such as lithium application or sealers, for instance. One approach that has been quite interesting is the fact that you can actually install all those different monitoring tools in at the same location on a concrete element. So you can measure the cracking index, the expansion, and just beside the those patterns for evaluating cracking and expansion, you can measure the actual temperature and humidity condition, as you can see in the different elements here. Non-destructive testing has been proposed also for evaluating the internal condition of concrete showing surface cracking that was or attributed or not to ASR. So as part of the Federal Highway funded project, a team from the University of Sherbrooke has been using different tools for evaluating the condition of concrete affected by ASR. At this stage, I would say that there is limited information on the real effectiveness of non-destructive testing. We're making a lot of progress in determining whether or not different techniques can be used for that. So the research is in progress, really. This sketch here demonstrates the use of the impact echo test on a bridge structure in the state of Maine. What we found from different points of testing on the barrier wall, not on the barrier, but the wing wall and the abutment wall, was that there was a lot more questionable quality concrete in the area of the concrete that is exposed to moisture compared to the other parts of the structure. So the impact echo seemed indeed able to recognize the internal condition of the concrete in that case. So I have discussed a few tools for the in-situ monitoring. Now let's look at some more recent development in terms of advanced laboratory investigations for ASR quantification and prognosis. The first tool that has been used in the past decade, I would say, or a couple of decades, is what we call the damage rating index. This damage rating index is a quantitative petrographic procedure that is carried out on a polished concrete section that has been extracted from the evaluated structure. And the polished section is actually examined under the stereobinocular microscope at a magnification of about 15-16 times. So when a polished section has been prepared, the procedure for running the damage rating index is actually to draw a grid at the surface of the polished section. It's that grid will be composed of 1 centimeter square at the squares at the surface of the polished section, and the petrographer will examine each square in order to count the presence of a number of petrographic features of deterioration, cracking in the coarse aggregate, either filled with gel or not, cracking in the cement paste, filled with gel or not, reaction rims around the aggregate particle, gel in cracks in voids of the cement paste, and so on. So all those squares are examined in order to determine the presence of those features, and then the counts of each of those features over a 100 centimeter square section will be multiplied by a number of weighing factors that have been proposed in order to have a relative importance determination of those different features. I mean, for instance, that when you have, for example, closed cracks in coarse aggregate, those are not considered as very, very critical features of ASR, so a multiplying factor of 0.25 is given to the counts of the closed cracks. But when you have open cracks in the coarse aggregate, a multiplying factor of 4 is given because this is much more important in terms of durability and feature of concrete deterioration. So when the counts have been determined like that, the data from the petrographic examination can be compiled and put on a chart like this, which illustrates the presence of the different features of deterioration. As you can see here, the features of deterioration that are to be determined by petrographers can be observed, all of them in this 1 centimeter square, where you have cracks in the aggregate particle with gel in voids of the cement paste, gel in cracks of the cement paste. So all of those have been compiled and put into a chart like that, and the compilation like that can be used to determine the difference between cores that can be taken from different portions of the concrete structure, or if you run the test after every year, every second year, then you can go back and plot the new result on a chart like that and determine whether there is any progress in the deterioration, since this is a quantitative determination of damage. Just going to give you an example here of the application of the damage rating index. This is in the state of Maine, the Interstate 395 corridor in Bangor, Brewer. We have examined a number of bridges along this I-395, and I'm going to show you some result of this bridge here, which is the I-395 over Main Street. This is Main Street here, and the interstate is over here. So cores were taken in the early stage of the project. Cores were taken under the bridge deck, just at the corner of the deck, and also in the wing wall here. You can see the difference of the condition of the concrete under the bridge deck. There's basically no cracking whatsoever. But in the wing wall that is exposed to moisture, there's a fair amount of cracking that can be observed there. So cores were taken, examined in the laboratory using the damage rating index. And as you can see here on this slide, there was a fair difference between the concrete that is exposed to moisture and the concrete that is protected from moisture under the bridge deck. In the concrete that is affected by ASR, you can see a lot of cracking in the aggregate particle. As you can see here, open cracks and crack running in the cement paste between aggregate particles from one another, as you can see. But for the concrete that is protected from moisture, you see basically almost no cracking in the aggregate particle, maybe in some of them, but very little cracking in the cement paste and the aggregate particle. So having a tool that is quantitative like this allows to make a quantitative determination or difference between those two concrete cores. So other tools than mechanical test, than petrographic examination can be used for determining the condition of the concrete. Mechanical testing can be used. The mechanical properties of concrete affected by ASR are not necessarily affected similarly by the process. The mechanical property that is the most affected by ASR is modulus of elasticity, and the less affected is compressive strength. This is illustrated on this graph here, where we see a plot of the expansion of concrete specimen incorporating reactive limestone aggregate and non-reactive limestone aggregate. So specimens were made, concrete cylinder, and at specific ages, the specimens were taken out of the testing condition and were tested in the laboratory for their mechanical property. So you can see here that we have high expansion for the reactive concrete and very little expansion for the non-reactive concrete. So the mechanical properties here, you can see that the ultrasonic pulse velocity was very little affected by the cracking due to ASR, even for expansion ranging up to 0.25%. The compressive strength was affected only when the expansion was quite high, over almost 0.2%. Splitting tensile strength was more affected by than compressive strength at the same expansion level, but both compressive strength and splitting tensile strength were affected when very high expansions were obtained. But the most rapidly affected property was modulus of elasticity. As you can see here, shortly after expansion has occurred due to ASR, the modulus of elasticity actually was reduced extensively due to the internal cracking by ASR. So knowing that, in the early 1990s, a group of engineers have proposed a tool which is called the stiffness damage test, SDT, that consists in imposing a number of cycles of loading, unloading up to a certain stress or a certain load to concrete cores that were taken out of the concrete structures. So this test is basically a very interesting test where you do basically a modulus of elasticity, and this graph shows the progress of the stress strain curve as a function of the expansion of the concrete that is being tested. So you can see that when you have very low expansion, all the curves actually fall on the same pattern, but with the progress of expansion, you can see that there is an area that is being generated under the first cycle of loading unloading. This actually corresponds to the energy that is being dissipated in the system, in the concrete, in order to close the cracks that have been generated by ASR. So two parameters, so in that test, two parameters were found to actually provide very interesting information about the extent of ASR in concrete affected by this mechanism. The first tool is the area under the first cycle of loading unloading, and the second parameter is the plastic deformation of the concrete during either the first cycle or the 5 cycles of testing. So those two tools have been used extensively to characterize deterioration due to ASR. And I'm going to give you an example of the application of those tools. Once again, for the structure in Maine, the I-395. So once again, the cores that were taken out of the different portions of that bridge were subjected to the SDT. Here you see the results for the core that was taken under the bridge deck, and here's the result for the core that were taken on the exposed portion and cracked portion of the structure. So as you can see here, this is the dissipated energy in the system. This is the first tool I was mentioning. So you can see on the average of the 3 cores that were tested, a fair difference between the uncracked here and the cracked concrete, and the difference is due to the effect of ASR. Similarly, for the plastic deformation as well as the modulus of elasticity that can be obtained from the unloading, the loading and unloading curves for the average of the second and third cycle, you see a fair difference between the uncracked here and the cracked concrete, uncracked concrete and the cracked concrete. So this SDT is still a tool that is being investigated in the laboratory, and more we're trying to develop additional information that can be used by practitioners. But so far, the application of that tool to concrete structure as part of the Federal Highway project has been quite successful. A tool that is being used also in different labs for evaluating the potential for future deterioration due to ASR is the expansion test on cores. In this test, cores that are being extracted from concrete structure are actually measured for their dimension as well as their mass, and the cores are being kept in the same condition as for the concrete prism test, 38 degrees Celsius or 100 degree Fahrenheit and 100% relative humidity. And the changes in mass and expansion is monitored over time in the laboratory. So here you have a plot of the mass variation and the expansion of cores that were affected by ASR. So this is a test that, as I said, has been used and is commonly being used by engineers in order to determine what is the potential for future expansion. Unfortunately, it's not a test that is easy to deal with. The main reason for that is that when you extract the core from the structure, obviously you take the core, the concrete, from a condition that is very different from the condition in which you're placing the core in the laboratory. So under those differences in condition, at the beginning there would be some expansion and moisture uptake that would be related to the change of condition. And then after a certain equilibrium in moisture and expansion, the residual expansion due to ASR will start. The determination of the time where to start the residual expansion test is not easy to do and will depend on the condition of the concrete structure. So although this test is being used, you know, you have to be very careful with the interpretation of the data. But I wanted to mention about it because it's being used quite extensively. And in this document, the report for the diagnosis and prognosis of ASR, we provide a table here to help the engineers for the interpretation of the result of the concrete core expansion test. So depending on the test, on the expansion rate that you measure over a 1-year testing period, the residual expansion of the concrete would be considered as negligible to very high. So this is based on testing that has been carried out on cores extracted from concrete structures. Another tool that is also used for evaluating the potential for future expansion is the determination of the water-soluble alkali content. As was mentioned by Professor Thomas in the first presentation of this series of webinar, the amount of alkalis which relates to the pH of the pore solution in concrete is a critical factor for the development and the maintenance of ASR in concrete. So one tool that can be used to determine whether the alkali content in the concrete is still high enough to maintain the expansion is to determine the residual water content, water-soluble alkali content in the concrete. This can be done by grinding to very fine powder a piece of the concrete core and then taking about 10 grams of that powder and boiling that 10 grams in water for about 10 minutes to leave the solution to stand overnight, and then filter the solution and analyze the solution for sodium and potassium in the solution. And this is giving the actual residual water soluble alkali content in the concrete. And as part of this document, we're providing once again a tool, a table for the interpretation of the results of the residual water-soluble alkali content to determine if the potential for future expansion is very low or very high, depending on the amount of alkalis that you measure in the test. So this whole management approach, as I have explained during the past hour, is really using a number of tools. Those tools are not necessarily at this time standardized, and they're not in most cases, but they are being used right now and evaluated for providing in the future better information for engineers. But for the final interpretation of the results, it is important to determine what is the critical structural effect of ASR in concrete members. And in the guideline document, we are providing some suggestions in order to do the interpretation of the results of testing, especially the residual expansion testing. In the case of reinforced concrete members, such as in bridge structures, the critical parameter that we consider is the expansion reached to date. Why is that? It's because the problem in reinforced concrete structure is really the number of years before the reinforcing steel could exceed the elasticity limit. And According to the literature, this could occur when the expansion of the concrete element has reached about 0.2% and above. So depending on the expansion reached to date and the rate of expansion, then the engineers will need to take some decision as a function of the expansion that has been reached at the time of the inspection and the rate of expansion to determine how many years are left before we exceed this 0.2% expansion, and some structural evaluation need to be done. Similarly, for concrete pavement, the critical parameter suggested is the current expansion rate, because in pavement, the critical factor is the development of spalling at joint, because this becomes a real security issue. And so the engineers need to determine how many years are left before the joints are closed because of the expansive process due to ASR, and then spalling will occur. So the use of in situ monitoring of expansion and also evaluation of the potential expansion through expansion on cores can actually provide tools to determine the current expansion rate, to determine how many years are left before closure of joints, and then depending on those years left, there will be some decisions to be taken by the engineers to decide what to do, as will be discussed also by Professor Folliard in the next presentation. So for concluding remarks, in this presentation I gave you some information on tools that can be used for the diagnosis and prognosis of ASR in transportation structure. The first process generally consists in the visual survey or the condition survey of the concrete structure to determine the presence of typical symptoms of AR. That is followed by sampling and petrographic examination on cores to confirm the presence or not of ASR and the different mechanism involved. And then if there's a need to actually obtain more information about the progress of ASR with time, which is prognosis, then there are a number of tools that were presented also, the determination of the cracking index through in situ monitoring, the determination of the stiffness damage, the use of the stiffness damage test to see the deterioration of the mechanical properties of the concrete, expansion test on cores, and the determination of the water-soluble alkali content. So all those tests, although they are not standardized at this stage, are probably the tools that are the most recent developed in order to provide information for prognosis. And all the detailed approach that has been presented today is actually given in greater detail in this document that you can obtain from the Federal Highway website. So thank you, and I'll be available to answer your questions right now.
Okay, thank you, Dr. Fournier, and we will go over a few questions that have been submitted now. I'm also going to invite Dr. Folliard on the line in case he wants to provide input on any of these questions as well. The first question, is the discoloration in the AAR damage efflorescence, or is it a different product?
The discoloration or the brownish staining that we see at the surface of the of concrete structure is, in many cases, is actually efflorescence and or alkali silica gel affected by carbonation. So the exposure to the CO2 of the atmosphere is actually going to contribute to the development of that staining. Whether or not there will be ASR reaction products, alkali silica gel present in that in the surface exudation, if you like, that will need to be determined by taking a sample of the exudation of the material at the surface and run some laboratory tests, chemical analysis or petrographic examination that can be used to confirm the presence or not of alkali silica reaction product at the surface of the affected element.
Okay, thank you. And the next question is, please clarify if there will always be reactive products at the cracks. This is important if I am to have a clear dichotomy between ASR and structurally induced cracks that would also go through the aggregates.
That's a very good question. Actually, ASR is a process where the expansion will be generated by the production of gel. The alkali silica gel, the amount of gel that you will find in the concrete will vary a lot from one aggregate to another. Will vary a lot according to the composition of the concrete. For instance, the amount of alkalis in the system that will generate more expansion, more rapid expansion and reaction. When you prepare your samples also for evaluation in the laboratory, if you use polished section, the process of sample preparation can actually also contribute at extracting the gel from the core. So it is possible sometimes that you see open cracks that are not necessarily filled with gel. It doesn't mean that the gel was not there before you prepared your sample, so you have to be very careful with that. But overall, I would say that normally gel will be present when you have ASR, and sometimes you need to go very finely to the scanning electron microscope to see that gel. If you have structurally induced cracks, then those cracks may not contain gel if there is no reactive aggregate in the concrete.
Okay, very good. Next question. Regarding slide 34, the gel is present in the paste and voids, but not within the aggregate. How would you explain this?
Let me go back to slide 34. Maybe I can escape that. Oh, okay. This one, I believe, 34. So, yeah, in this case here, you see there is a. Whoop, I use my. There is a. Going to use the tool. You can see the secondary product in the paste indeed there at the border. You can see open cracks here. So there was possibly alkali silica gel present here, and that gel may have been leached out during sample preparation, because you see that the crack is fairly open there. So when you have open cracks like that, this is more, those cracks are more prone to for the gel to disappear during sample preparation. But this actual slide here is a very limited portion of the concrete. So there might be other areas where the gel will actually run into the aggregate particle. So sometimes the gel will pass at the border of the aggregate particle. In this case, it is happening like that. But as I said, generally speaking, when you have an alkali silica reactive material, you will see cracks in the aggregate particle. The presence of gel will be a function of the reactivity of the aggregate and also, unfortunately, sample preparation.
Okay, thank you. The next question, as you show the ASR gel filling the air entrainment voids, does this then eliminate the benefit of air entrainment in the concrete?
Yeah, this has been mentioned as a possibility. The air voids that are the most useful for freeze-stop prevention are the very, very fine air voids. So those air voids are not necessarily those that we see being filled by ASR reaction products. The voids that we see that are being filled by products, like for instance in this slide here, are those that are met by cracks, where the gel that is running here through the cracks will be actually dumped into the air void at this stage. So in general, I would say that not all the voids that you can see here will be filled with the gel, because most of the time what you see actually is gel being found along the cracks, as you can see in this slide here. But you will not necessarily have gel oozing out of the reactive particle to fill the paste of gel around, not at least to a very large extent. The gel is very much concentrated in the cracks. So whether or not it's going to deleteriously affect the freeze-thaw performance of the concrete, possibly not to the extent of the cracking itself, because obviously when the water will freeze and thaw in the cracks generated by ASR, this is going to be the main mechanism responsible or contributing to deterioration.
Okay, and as a follow-up to that, if the concrete is designed with expanded shale, clay, or slate lightweight aggregates, will the voids in these aggregates provide a space for the ASR gel to go, thereby protecting the air entrainment voids?
As I just said, the gel is, generally speaking, and based on the evaluation of a fairly large number of concrete specimens, the gel is generally limited to the cracks and is not necessarily oozing out of the reactive particle. So the presence of the lightweight aggregate particle there may not be considered as much as a safety area for the gel to relieve expensive pressure, because the gel will not necessarily reach those particles, but the gel will be concentrated in the cracks per se. So I would doubt that the presence of those lightweight aggregate particles, which have a high porosity, will really be will be considered as a preventive action against ASR expansion.
Okay, very well. The next question is, when comparing the water-soluble alkalis in concrete, is the amount of alkali present in concrete containing cement only noticeably greater than concrete containing high volumes of SCM?
Yes, generally speaking, the amount, the water-soluble alkali content that you will measure will be the alkalis readily available from the cement. The alkalis incorporated in the supplementary cementing materials in general will not be released during that test. But once again, this is still to be proven in a large extent, because right now we have not carried out a lot of testing for determining the water soluble alkali content in concrete incorporating large amounts of SCM. The main reason being that those that are containing such a large amount of SCM generally don't necessarily show signs of ASR. So we have been concentrating on concretes affected by ASR, and those generally don't contain much SCMs. So in that sense, I think there is a need for more work to about the effect of that test on concrete incorporating lots of SCMs.
Okay, next question is there a documented correlation between ASR occurrence and concrete pavement buckling?
I can't really answer that question. The problem, I would say, is the quantification of the expansion. If such documents are available, those might be in reports that are not necessarily public. To my knowledge, I have not seen such a documented, I would say, in terms of quantitative assessment. We have been over the years installing monitoring equipment on pavements in different states in order to come up with that kind of information, try to correlate with numbers supporting that the expansion process and the closure of joints and the and buckling, as you said. So we know that it has been happening from observing it to happen, but numbers per se, I am not aware personally of that. I don't know if Kevin, if he's online, if he has some information.
Yes, thank you, Benoit. I'm not aware of any specific cases where ASR has been implicated directly in pavement buckling. I have heard anecdotally some cases with CRCP pavements where they've had some distress that was somewhat sudden, and that was potentially due to ASR, but I don't think there's any definitive proof. Most of the issues that we observe with pavements tend to be degradation at the joints, which ends up being kind of the end game in terms of serviceability. But in terms of the actual buckling, I'm not aware of any specific cases where that's occurred.
Okay, thank you both. We'll move to the next question. Do you see more serious deterioration from coarse aggregate ASR or fine aggregate ASR?
That's a good question. I would say we can see both happening and create extensive problems. In a number of cases in the past, we have been considering pretty much only ASR happening in the coarse aggregate. This is very much the experience that we have in Canada. But having been involved in the Federal Highway project for the past few years, I have examined cores from concrete structures where the ASR is definitely being generated by the sand, and distress, extensive distress has been found in the field. And Kevin has a lot of experience of testing sands, reactive sands, in his exposure site. So maybe you can comment on that as well, Kevin.
Well, I would agree with Ben. We've seen cases both where the damage comes from the coarse aggregate and the fine aggregate. And not only that, we often see that the deterioration might come from just, say, a single size fraction within an aggregate. So, you know, I would say we've seen a whole range from the relatively small particles reacting all the way to the large coarse aggregates, and any of them can be damaging to the concrete.
Okay, thank you. The next question is, how can you tell visually if the cracks are ASR or DEF cracks?
Basically, it is based on a petrographic examination of concrete cores. First of all, obviously the source of the problem is not the same. In the case of ASR, it would be related to alkali silicate gel. In the case of the DEF, it's related to the formation of secondary yttrangite in the concrete. So I would say, visually speaking, when you look at the structure, it may look similar to some extent, but you need to absolutely do petrographic examination in order to determine the source of the problem.
Okay, the next question. How does fly ash or slag mitigate ASR?
This topic has been discussed last week during the webinar last week. Basically, to make a long story short, the supplementary cementing materials such as fly ash, slag, silica fume contribute at reducing at reducing the pH, if you like, of the pore solution within the concrete. Since ASR expansion is very much related to pH, by using different proportions of different types of SCMs, the pH in the pore solution will be reduced, and this will reduce the progress of ASR. Also, these products will make concrete much more impermeable to moisture ingress, and moisture being a very critical factor for ASR. This is also one way for the SCMs to provide protection against ASR.
Okay, and with that, we're going to need to move on to Dr. Folliard's presentation, so I will hand over the screen to him.
Okay, good afternoon. It's my pleasure to be giving this webinar today, and it's good to be following up on Dr. Fournier's presentation because it's a natural segue here. What I'll be talking about today will be mitigation measures that have been applied to ASR affected structures. And as I said, it's a pretty good and logical follow-up to Benoit's presentation because what he just discussed was focusing on the diagnosis and prognosis of AAR in transportation structures. And then I'll be talking about what options might be available to owners to deal with such structures. Both of these topics that Dr. Fournier covered and that I'm about to cover are part of that report on the diagnosis, prognosis, and mitigation of ASR in transportation structures, which is available from the Federal Highway Administration. Before I get into some of the specific case studies and some of the technical background on the various techniques, I just wanted to give kind of a snapshot on the overall program that we've been involved with for the last several years, which is funded by the FHWA. On the slide here, you see the various field trials that are still ongoing in various states. And you can see here that we've covered quite a few different states. We've also covered quite a few different types of structures, from pavements to bridges to median barriers. And in addition, we've looked at a range of different mitigation or or repair techniques, such as the use of silane sealers, lithium nitrate, FRP wrap for confining ASR affected columns, as well as some other methods of treating structures. Throughout today's presentation, I'll refer to several of these studies as we go along. And I will also mention that by the end of 2013, we will have a final report which will summarize all the results to date. Having said that, it's important to realize that any of these structures that we're treating and monitoring will take several years to really see whether or not the treatments are effective or not. And in many cases, time will tell, and it will be way beyond the point that we write this final report. But that is the nature of alkali silica reaction. So what we'll talk about now are kind of globally how we can deal with alkali silica reaction in field structures. And we can think of it simply as on the left side of the slide here, we can talk about treating the cause of ASR. And on the right side, we can talk about treating the actual symptoms of ASR. So when we're talking about treating the cause, I'll go through several of these in detail, but just in terms of this slide, there's a couple of chemical treatments that can be considered. One is that theoretically one could treat a concrete structure by injecting CO2 into it, and the purpose of that kind of a treatment would be to reduce the pH of the concrete pore solution and thereby slow down or stop the dissolution of the silica and the expansion and cracking. However, this really isn't very feasible from a practical point of view, and also from a technical point of view. Carbonating concrete that has reinforcement in it would lead to corrosion, of course, and also injecting ASR affected concrete with pressurized gas could lead to additional microcracking. So this isn't something that we recommend nor that we have tried in the field, but it has been mentioned as a potential way to deal with structures. What we will discuss more today will be the use of lithium compounds. And lithium has received quite a bit of interest in say, the last 10 or 15 years. And that's because previous laboratory work showed that if one could take small laboratory specimens and dry them out and then soak them in lithium nitrate solution to ensure a pretty high degree of saturation, that concrete would then would expand much less than an untreated specimen. So this is why we're quite interested in lithium as a technology. And essentially what lithium has the ability to do is to react with the ASR gel and essentially make it so that it no longer expands or expands much less. So we'll show that some field trials involved with lithium. We'll spend quite a bit of time talking about drying out concrete through primarily the use of sealers, but I'll also talk about some other potential methods of drying the concrete out. And here the goal is to lower the relative humidity and to below a point where ASR will no longer be a driving factor. If we look at the right side of the slide, we have the treatments of the symptoms, and you'll see here that some of those involve just crack filling. This is typically done with a flexible caulking material, and it's often done for aesthetics or particularly to try to protect the concrete from chlorides penetrating in, or perhaps from preventing water from penetrating in cold environments where freeze-thaw might create some issues in the cracked portions of the concrete. Other things we can do and that will be described will be to restrain the concrete. In other words, to make the concrete that's already expand essentially go into compression by confining it, typically externally. And this does not stop ASR. The gel is still there. It still tries to expand, but we're going to physically try to stop it from expanding. And lastly, I'll talk at the end of the presentation about some techniques where we try to relieve the stresses that form in an ASR-affected structure, and I'll give a couple of case studies on those as well. So globally, that's what I'll be talking about, and I'll start first by just kind of listing the various methods that I'll describe specifically. You'll see here that the first 4 bullet points on the slide are all aimed at lowering the relative humidity in concrete, and I'll discuss those first. We'll then discuss various field trials of applying lithium to field structures, spend a little bit of time talking about using external restraint, and also trying to relieve stress through saw cutting or slot cutting. So what I'll discuss first is the technical justification for trying to reduce the relative humidity in concrete. It's been shown by various researchers that if one can reduce the internal relative humidity in concrete below some certain threshold, that the future potential for ASR can be significantly reduced. This graph here shows a series of different reactive aggregates that were for which concrete was made, and each of these concretes were then stored at different relative humidity conditions. And what you can see here is if you can reduce the internal relative humidity in concrete below about 80%, that the future expansion will be significantly reduced. This 80% threshold number is not set in stone, but there's quite a bit of data out there that shows that if you can get below 80%, most reactive aggregates will exhibit much less future expansion. So this is our driving force. ASR needs water. The gel needs moisture to expand, and the availability of water allows the various processes to occur at a much quicker rate. So there are certain things we can try to do to field structures, and one of the first steps we should always take when ASR is suspected or confirmed in the structure is to do anything that's feasible to improve the drainage and get the water away from the structure that's affected by ASR. Here's an example of a bridge column that was sitting below a bridge deck where the joint had been leaking for several years, so the water was being deposited directly on the top of the column. And in addition, shown here on the right, you can see an integral drain pipe that was intended to take the water from the bridge deck through the column and then drain it away through the subgrade. But we noticed in this bridge that drain pipe had been clogged for some time. So simple fixes for something like this would be to improve the drainage from the bridge deck above and to divert the water away from the column. In many cases, this will have a very significant impact on ASR, and whenever it's feasible, this should be the first line of defense. But there will be cases where it's not possible to improve the inherent drainage on the structure, and we'll then take a next step in trying to dry the concrete out. And based on quite a bit of experience in the lab in the field, it's been learned that one of the most effective ways of lowering the internal humidity is to apply some kind of a breathable membrane to the surface of the concrete, or a breathable coating. This example shows the application of silane. Silane is a product that will, when you apply it topically to concrete, it will penetrate in just a couple, 3 millimeters or so, but it will react chemically with the concrete substrate, and it will form a hydrophobic barrier, and that hydrophobic barrier will prevent liquid water from coming in, but because it's a breathable barrier, it will allow the vapor inside the concrete to escape with time. And this is very critical. It's important to make sure that when we try to dry concrete out, we can allow that internal vapor to get out. And you'll see with some data in a little while here that in cases where you use an impermeable membrane, you'll trap the moisture inside and have little impact at all on expansion. And in fact, it's possible you could make the situation worse. This slide does not suggest that silane is the only product that would work. There's a range of different products that work, but the key here is that the product must react with the concrete surface to form a durable coating, and that it must prevent water from getting in while allowing the vapor to get out. So there have been several case studies that have been done over the years with different products. This slide here shows data from the Hanshin Expressway in Japan, and these ASR affected columns were expanding considerably. And in 1983, a series of different treatments were applied to the columns. And what you can see here is that on the graph on the right-hand side shows that that silane was applied, as well as epoxy, polymer cement, epoxy, and acrylic. And what you can see over the 7-year monitoring period is that the silanes were very effective in reducing the expansion of these columns. This was confirmed by the researchers by demonstrating that the internal humidity of the column was dropped considerably. The other treatments that were used, particularly the acrylic and the epoxy, had very little effect on expansion because these formed impermeable, non-breathable membranes and therefore were not very effective in lowering the relative humidity. Now, it's interesting to think that a very large column, such as the one shown on the slide, could actually be positively affected by the use of silane when it's such a large element. And the thinking here is that the bulk of this column is heavily reinforced, and within that reinforced column cage, there's probably enough reinforcement in there to physically confine expansion. And it's quite likely that this silane treatment primarily affected the concrete outside of that cage region and was able to then reduce the expansion of the column itself. There's been quite a bit of work done in North America on the application of silanes. Here's an example from our federal highway project where we treated several miles worth of highway barriers just outside of Boston with silanes. We also used other products such as lithium, which will be described later. Silane can be topically applied as shown in this photo, so it's not very difficult in terms of resources. The Canadian experience has been very positive. There was a comprehensive study that was that was done up in Canada a few years back, and this is a photograph showing the left-hand side was an untreated portion of the barrier wall, and on the right-hand side you can see the silane treated section. It's a very vivid effect visually because once the concrete dries out, the gel that's at the near surface also dries out, and that's the gel that typically would become carbonated and leave that very diagnostic kind of staining that we see with ASR affected concrete. So you can see here from a visual point of view, the silane was quite effective, and I'll show you in the next couple slides that it was also very effective in A, reducing expansion, in B, reducing internal relative humidity. So here's the monitoring that was done on these barriers. It included expansion measurements, also internal relative humidity measurements, and crack mapping as well. And what we can show here with this graph is on the upper portion of the graph, you have the unsealed control section, And this control section here, shown right here, is maintains a very high relative humidity during the monitoring period. You'll see that it nominally stays between 85 and 90%. The barriers that were treated with silane, you can see in the lower curve, tended to reduce over time in terms of humidity, and after say 6 years of monitoring, you can see that the humidities were well below the 80% threshold that I showed a few graphs ago. Now, one thing you'll notice here is that these graphs are not perfect lines, and that's because relative humidity will vary throughout the year, and it really reinforces the fact that you need several years of monitoring to really get over any of these variations that occur due to ambient conditions and temperature and moisture conditions within the concrete. But clearly, this is very strong evidence that silanes were effective in reducing the relative humidity. In addition to reducing the humidity, we can see here that the treated specimens did no longer expand during the course of the monitoring. First, let's look at the controls up here. And this graph is showing expansion on the y-axis versus time on the x-axis. This top line here shows the general increase in expansion during the course of the monitoring for the untreated specimens. And if you look at the middle line here, this is the length change of the concrete that was treated with silanes, and you can see actually during the 6-year monitoring program that it actually resulted in a bulk shrinkage of the overall concrete. So it's very good proof that it was not only possible to lower the humidity, but also the expansion for these barriers. These barriers have now been out in the field for well over 10 or 15 years, and the performance still seems to be holding up in terms of keeping the expansion down and the humidity down. Coming back to the experience here as part of the Federal Highway project, we're happy to report that we've had quite similar results. Here's a photograph showing the control on the left-hand side and the silane-treated barriers on the right-hand side. I won't go into the data here today, but we've also shown that the relative humidities have nominally dropped below 80% and that the expansion has leveled off or even stopped for the silane-treated sections. Now, one point that I'd like to make about this is that highway barriers like this represent perfect candidates for silane treatments. They're slender, they can be treated on both sides, and when we treat concrete with silane, what we notice is that we tend to lower the relative humidity from the outside in, and it probably only drops the humidity in the outer, say, couple of inches of the concrete, maybe 3 inches. Well, if you have a relatively thin barrier like this and you treat both sides of it, then you can actually reduce the relative humidity across the entire cross-section. And that helps to explain why the silane treatments are so effective on these type of barriers. Now, silanes will not always work. We know that for sure. If it's concrete below grade, there's very little you can do in terms of making silanes work well. And we're not sure about other situations. Sorry, before I move on to lithium, I did want to say that we're working on a couple of projects. For instance, in Arkansas, we've treated a pavement section. And in Maine and Vermont, we've treated wing walls of bridges that have backfill on the other side. It remains to be seen whether or not silanes will work in cases where you don't have control of the moisture coming from the bottom side or the back side. But I do believe with the instrumentation we have in place that we'll be able to come up with a better feeling for when silanes are appropriate and when they won't work so well. But that will all be in the final report. So let's switch gears now to lithium treatment. And what I'll do is give brief case studies on work that we've done in Idaho, Massachusetts, and Texas. And again, the motivation behind this was based on lab work that was done in the 80s that showed that small laboratory specimens, when dried out and then soaked in lithium nitrate, could reduce future expansion compared to control specimens. So we do know that lithium can affect the nature of the gel and render it non-expansive or considerably reduce the expansion. So prior to us starting this work in the early 2000s with Federal Highway, there had been quite a few applications of lithium applied in the United States. Most of these were done on pavements, a few on bridge decks, and the vast majority were topical applications where lithium was sprayed, typically with a DOT spray truck. Unfortunately, those previous projects had very little monitoring, and there's really no definitive proof as to whether or not the application of lithium had any advantages in the short or the long term. And that was the motivation behind this project, to go out in the field, apply lithium to real field structures, track the depth of penetration of lithium, and determine whether or not that's advantageous in terms of reducing expansion. So the first one I'll start with was in Idaho. We did treatments back there about 8.5 years ago or so. And this was a pavement on I-94 in Mountain Home, Idaho that had suffered considerable ASR damage. In this field study, we were able to treat 3 different levels of distress within the pavement that we considered to be low, moderate, and high. And within each of those test sections, we did various numbers of treatments, either 1, 2, or 3, in terms of a topical application of lithium. Each of our applications were based on the manufacturer's recommended application rate, which is on the order of 6 gallons per 1,000 square feet. And you can see here with the photo on the right, the spray truck that was used to treat this pavement in Idaho. So after the treatment of this pavement, our team spent quite a bit of time monitoring the pavement, and particularly focusing on the depth of penetration of the lithium into the concrete itself. Let's look at some of the data from the depths of penetration. This slide here shows on the y-axis the lithium concentration expressed in parts per million. You'll see here that the red dashed line at 100 ppm, that's the amount of lithium that we estimate is needed to significantly reduce expansion in concrete based on prior work. And you'll see this dashed red line a few other times today. And on the x-axis, you see the depth with 0 being the surface of the pavement and working its way into the pavement. What we did is we took cores from different sections, and we intentionally sought out cores that would go through cracks as well as those that were away from cracks from each of the damaged regions. This data here shows that the depths of penetration range from about 1/4 or 1/2 millimeter upwards to about 3 millimeters. So in general, less than 1/8 of an inch of penetration. And this was really useful information to have, because this pavement is 12 or 14 inch thick concrete pavement, and we've shown here from this data that we're only getting depths of penetration into the outer 1/8 of an inch. Now typically that surface concrete in the outer 1/8 of an inch would have been the concrete that would have already carbonated over the years, and the pH would have already essentially suppressed ASR in that upper region. So based on this data, the conclusion here is that the lithium penetrated very little into the concrete. And lithium can only protect against ASR in the portions of the concrete at which it penetrates in a concentration above this proposed threshold. It's not like silane, where silane only needs to penetrate in 2 or 3 millimeters in order to form a barrier that prevents water from getting in but allows vapor to get out. So based on this, we were a bit discouraged in terms of topical treatment of lithium. But we wanted to follow it up with some more controlled work in a laboratory environment. And what we did is we took full depth sections out of that I-94 pavement. We took it back to our lab in Austin, Texas, where we then subjected it to similar types of treatments under slightly more controlled conditions. We then cored the concrete and determined the lithium profile using profile grinding and flame photometry. This next graph shows the lithium penetration, and you can see I'm again using a red dashed line. The units here have changed, but the concept is the same. This is 0.01% lithium based on total mass of concrete. It's based on the same assumption as the previous slide. And what you see here, the depths of penetration were about the same as what were observed in the field, somewhere between 1 and 4 or 5 millimeters. So again, our ability to get lithium to penetrate into field structures with topical applications seems to be very, very limited, both when we've done it in the lab and in the field. And since we did this study about 8 or 9 years ago, our team has done quite a bit of follow-up work on it and have shown pretty definitively that topical treatments of lithium into mature field-type concrete results in a very similar lack of penetration. We also did topical applications of the highway barrier in Boston. This is the same barrier that I showed previously that showed very good results with regard to silane application. And what we did is we sprayed topically lithium nitrate, and we sprayed it 1 time, 2 times, all the way up to 4 times. And we also tried to vacuum it in under pressure by hiring a contractor who had done a lot of vacuum impregnation for concrete repair jobs in the past. I'll first show the data for the topical application and then that for the vacuum impregnation technique. This data here shows again, we have concentration of lithium on the y-axis versus depth on the x-axis. And what you see here from this is one of the barriers that was sprayed the most number of times, a total of 4 applications. And you can see here, once again, the depth of penetration is essentially negligible. It's only 1 or 2 millimeters. And again, this would be the surface concrete or the near surface concrete that more than likely would have already carbonated in the environment, dropping the pH below the value that would really cause ASR. So again, it's proof that topical application is not very effective in field structures. But as I mentioned, we also wanted to be more aggressive in our means of driving lithium in, especially since we saw that we were unsuccessful with any of our topical applications in the lab or the field. So as I mentioned, we hired a contractor who had done a lot of vacuum impregnation work over the years, and they applied lithium by pulling vacuum across the barrier, and in some cases left a vacuum in place for well over 8 hours. And we then cored from these test sections and measured the lithium concentration, which I'll show in this graph. And here you can see that the 2 different vacuum treatments are shown here, and in both cases our depth of penetration, again using some threshold value of lithium concentration here, that we're on the order of somewhere between 2 and 4 millimeters. So what we show here is that it's also very difficult to use a vacuum to drive lithium into field structures. And having spent quite a bit of time looking at this issue over the last 10 years, it's very consistent with other materials that have been attempted to be vacuumed into concrete. And the challenge here is if the pores are already saturated with water, it's virtually impossible to drive any liquid that will displace the moisture in the concrete already. And it's generally not feasible in field structures to dry the concrete adequately enough so that it will be more amenable to receiving the liquid through a vacuum technique. So we'll come back to some additional vacuum trials in just a minute. But in a nutshell, our study with the Jersey barriers outside of Boston showed that the application of silane was quite successful, but lithium had because of the lack of penetration, had no effect whatsoever on the future expansion of the barriers. We then turned our sights on one last field trial that I'll discuss today with regard to lithium, and this was a series of ASR-affected columns in Houston, Texas. And with our experience in pocket already from the Idaho and Massachusetts trials, we had already decided that we wouldn't spend any more resources on topical application of lithium. And although our vacuum technique wasn't very effective in Boston, we wanted to give it one more shot. And again, what we did in this case is we brought in contractors who have long experience with both vacuum treatment as well as electrochemical treatment, which I'll describe in a little bit more detail. Within this trial, I won't discuss it today, but we also included the application of silane. And in the study, we looked at silane both on a sandblasted surface to remove the surface paint, as well as the application of silane on a painted surface. Although I won't show the data because of a lack of time today, we did prove here that silanes were effective in reducing relative humidity, even when applied over a breathable appearance paint. So that could be promising for highway departments that are wanting to apply silane over a painted surface, but it first needs to be checked to make sure that the silane will penetrate beyond that paint layer so that it can react with the concrete substrate. So let's spend a little bit more time again here on the lithium side, looking at the vacuum treatment and the electrochemical treatment. So we hired a contractor here who had previous experience with driving lithium into field structures. This shows the vacuum plate that was used to apply the lithium to the concrete. And the next slide here shows the results. Again, we have lithium on the y-axis versus depth on the x-axis. And what we were able to show here is that we were able to get penetrations a bit higher than the topical applications, but it was still limited to the outer, 6 to 8 millimeters of the concrete surface. So maybe the outer third of an inch was adequately treated by lithium. These columns, by the way, are on the order of, say, 8 to 10 foot in cross section. So we were able to get more lithium in, but it's probably, based on this work, not worth the added resources and the amount of time and money spent trying to drive the lithium in with the vacuum, because we were still able to only get in 7 or 8 millimeters. Let's look at the electrochemical treatment method. And the technique we used is a rather mature technique that has been used a lot in chloride contaminated slabs. And the approach in this case is to try to get the chloride out of an existing bridge deck. And the way it's done is with what's known as electrochemical treatment. What's done here is that you use an electrode, you drill in and tie into the rebar, and then you apply a current across the concrete. And the goal, apply a current between the electrode that's placed at the surface and the steel, which is at a couple of inches within the surface of the concrete. And the net effect of this approach is that the chlorides get driven out of the concrete and towards an electrolyte. And this is some kind of a cellulose blanket saturated with an electrolyte. And what that will do is that will absorb all the chlorides as it reaches the top surface of the concrete. This has been shown to be very successful in many field trials throughout North America and the world. But one thing that had been noticed years ago is that when you tie your electrolyte at the surface to the rebar, you end up actually turning the rebar into a cathode, and it produces hydroxyl ions at the surface of the steel. And there's concern here that when you produce these hydroxyl ions at the steel surface, that this will increase the pH of the concrete and potentially make ASR more of an issue at or near the rebar. So previous trials had been performed to try to counteract this effect, and the way that this was counteracted was by using lithium as the electrolyte in that top solution. And under this current, what ends up happening is at the same time that we drive the chlorides out of the concrete, we drive lithium ions into the concrete, and the goal then is to try to get to just counteract the hydroxyl concentration increase at the surface of the steel. But it should be mentioned that these efforts here primarily were based on driving chloride out of the bridge deck. Our goal in the Houston trial was there were no chlorides involved. Our only goal was to try to drive lithium into the concrete, and I'll show you how we did that in just a second. This just shows you one quick picture of the test setup here, but the contractor prepared the surface of the column, and then they put the electrolyte over the face of this column, and what's then done is lithium was pumped up to the top of the column where it would saturate this electrolytic blanket, and then the lithium would drip down the face of the concrete column where it would be collected by this gutter system, recycled, and brought back to the top of the concrete column. So this was the way we were able to get over gravity here. And then this outer electrolyte setup was then tied to the rebar, which was 2 inches into the column itself. Our current was then applied, and over the course of 6 to 8 weeks, and we were then able to go back in with the assistance of the contractor and select locations where we anticipated that the lithium concentrations might be the highest. So we picked them in these strategic areas, and then we did lithium profiling again, which I'll show next. So this graph might be a little confusing, but let me try to first give a little description. On the y-axis here, we have the percent concentration. In this case, we're not only tracking lithium, which is in light blue, but also sodium and potassium, which were already present in the concrete in the form of alkalis from the Portland cement. Once again, we have a red dashed line, which is the threshold lithium concentration above which we would expect to reduce expansion. And on the x-axis, we have the depth from the surface of the treated concrete. So the left-hand side is the face of the column, and as we go towards the right, it's shown here in millimeters, we go farther and farther away from the steel, the surface of the concrete, until we reach the surface of the steel that we had electrochemically coupled to. So this is essentially a 2-inch profile from the surface at the left to the rebar at the right. What was very encouraging about this trial is we were able to drive lithium all the way down to the surface of the steel at concentrations that were well above the proposed threshold value. Even 2 inches into the concrete, we were able to get 2 or 3 times the amount of lithium that was needed to typically control expansion. So that's the good news. Unfortunately, the other thing that we detected here, which we've now been able to confirm in other studies, is that when you produce those hydroxyl ions right near the surface of the steel, this will result in a net negative increase in the hydroxyl concentration, which has to be balanced by positive charges. And it ends up that the internal alkalis that are already in the concrete will actually redistribute and move towards the steel to satisfy the hydroxyl increase. And the concern here is we now seem to be redistributing and increasing the alkali concentration in the form of sodium potassium at the surface of the steel. So this is an issue that we're looking at still. We don't have enough data really to give any firm guidance on it, but certainly a word of caution at this point that we do need to first determine whether or not there will be any detrimental effects of the increase in sodium potassium concentration, which may outweigh any increase in the lithium concentration. But in terms of driving lithium into concrete, I think we do have some very good evidence here that electrochemical methods can be used. But again, we just have to be careful about this redistribution of internal alkalis. So this table here sums up the various field trials that I just discussed: the Idaho pavements, the Massachusetts barrier walls, and the Texas columns. And on the far right-hand side, you can see the typical depths of penetration. And as we saw with all the topical applications, it was very minimal and certainly not enough to result in any benefit. And the same could be said for the vacuum applications as well. But you know, the positive note here was we were able to drive the lithium all the way down to the surface of the steel. But again, we have to be careful with the possible effects of the sodium and potassium increase in that same region. So the results of all the lithium trials will be included in the final report. And so anyone that's more interested in this, we certainly would encourage you to look out for that publication coming out later this year. Now, one of the things we also did as part of the study is we wanted to look at, hypothetically, what could we do in terms of getting lithium into concrete and looking at kind of a best case scenario. And what we did is we cast 3 concrete blocks and stored them outdoors. The first one is shown here. And what I should say is all 3 blocks were identical. They all had a highly reactive sand from Texas, and they all had a very high alkali content. They were stored outdoors, and we had one control block that we monitored with regard to expansion and cracking. And you can see here the types of cracking we see on these blocks, which are quite extensive. In just a couple of minutes, I'll show you the expansion of this as well as the other 2 blocks. But this was a block that was cast as a control and just monitored and allowed to expand. In the second block, what we did is we constructed a dike on top of this block where we continuously ponded lithium nitrate solution for 8 months. Now we know this isn't practical in the field, but we at least wanted to see best case scenario, what if we could get the lithium in, and what the effects would be on the expansion. This here shows that the cracking actually was about the same or even worse when we had the continuous ponding for 8 months. I'll show you one other block where rather than ponding it continuously for 8 months, rather we sprayed it once a week for 32 weeks. And once again, you can see here that the cracking was quite extensive. So both blocks that were treated with lithium, whether continuously ponded or sprayed weekly, showed very little beneficial effects in terms of reduction in cracking. And when we look at the expansion, this is showing expansion on the y-axis versus time on the x-axis. Starting at the bottom here, this blue triangle here, or diamond, was the control block. And you can see that after about a year or so, it expanded almost 0.5%. The next data for the line above it was the block that was sprayed once a week for 32 days, for 32 weeks, I'm sorry. And lastly, the maroon triangle line shows the continuous ponding application. What's interesting to note is both of these blocks here expanded more than the control. And what this suggests is that when applying lithium nitrate repeatedly or continuously to concrete, it may be that since we're applying a solution that's 70% water and 30% lithium nitrate, it might be that the application of water is actually driving ASR more than the application of lithium is reducing expansion. It's just a guess, but it helps to explain these results. So now that we've talked about lithium applications, we're going to switch gears and talk about some other techniques. One of them is the application of restraint to try to control ASR. This is work done by LaRue in 1992, where he produced concrete and allowed specimens to expand vertically and then applied a uniaxial load vertically to try to stop the concrete from expanding. And what you can see here is if you just allowed the concrete to expand, it would expand in the course of a year or so about 0.7%. If you applied 1 megapascal, which is about 150 psi of a confining or a restraining load, that the expansion was reduced considerably. And when the restraint was increased all the way to 5 MPa, which is the same as 750 psi, the researchers were effectively able to stop expansion. So what this shows is that external application of restraint can provide enough mechanical force to prevent the concrete from expanding. Now, the more practical case here wouldn't be, say, applying a vertical load to a concrete structure to prevent ASR, but rather if one has a concrete column, and the question would become how much lateral confinement you would need, say in the form of an FRP wrap, in order to stop the concrete from expanding in that direction. We do have a field trial in New England right now where we're looking at just that, where we applied FRP to circular columns, and we are monitoring that with time. But there's been a lot of work done globally on this, and the results have been quite encouraging in terms of providing external restraint. Here's an example from some transmission towers in Quebec. These towers had suffered significant ASR damage, as is shown here in this photo, and there was concern particularly about the embedment of the superstructure into this footing here, and whether or not there might be any stability or structural issues. So what was decided was to do a series of different repairs to these towers, tower footings I should say, and let's look at a couple of these repairs. One was the use of removing the outer most damaged portion of those footings, then putting a rebar cage around the perimeter. And in the next slide, you'll see that what was done is formwork was then placed around the steel rebar there, and concrete was then placed in the formwork, and the formwork was subsequently removed, and eventually the backfill was put back in place. So that was one technique where an external form of restraint was applied, In this case, the restraint came from a reinforced concrete restraining ring around the towers themselves. In addition, this study also looked at post-tensioning techniques where instead of providing restraint along the entire perimeter of the element, rather the concrete was cored, post-tensioning rods were pushed through the concrete and then tightened to be post-tensioned. And again, the same intention here was to try to provide some form of external confinement or restraint on the ASR itself. Some of these treatments also included a membrane application to try to prevent water from getting in, and so various different trials were done in this one study. This graph here shows expansion on the y-axis versus time after treatment on the x-axis, and what you could see here is that the unrepaired footings or foundations continue to expand at quite a bit, 0.02% or so per year, which is quite considerable. When membranes were applied as the sole mechanism of repair, there was some reduction, so you can see that there was some benefit in reducing the water ingress into the concrete. But what tended to work most were the mechanical types of restraint that were applied, particularly the first example where I showed where the old concrete was removed, a circular rebar cage was placed on the outside, and then that was then encapsulated with new ASR resistant concrete. So this is just one example where external restraint was provided quite successfully. One thing I should mention, and perhaps I should have mentioned it at the beginning, is anytime you're dealing with the structure and you're considering applying external restraint to it, our group recommends very strongly that you consult with a structural engineer before any kind of retrofit is done, just to ensure that the structural performance of the structure is not compromised in any way. Here's some other towers that were repaired here as well, and you can see the before picture. You see large amounts of ASR gel and exudation. You see large cracks. And then after the repair and the placement of the external concrete ring, you can see the overall results here. This external restraint is not only limited to footings or foundation, like I've shown here, but it's also been applied to bridges as well. Here's a case where an arch bridge was retrofitted in Scotland through the use of steel plates and drilled through bolts. And you can see here where that repair was done. And this was both to try to mediate the ASR itself, but also to restore the structural integrity to this sensitive arch dam here that you see. And lastly, I'll just give a few examples of columns, which are probably the most common in terms of the application of external restraint. Here's an example from Australia where you had ASR-affected columns in a marine environment. And what was done here was a series of different repair jobs where you can see that here's a case where an external concrete jacket was applied. You can see them right here. And you can also see in the upper right-hand corner the application of FRP wraps themselves. Now, when considering FRP wraps, it's well established that those are most effective in circular elements because you can get general confinement around the entire element. It's very challenging if you have a square or rectangular column because most of the restraint is only being provided at the corner points. So again, every case is different, and again, we recommend that a structural engineer be brought in. But overall, there's been a wide number of these type field applications of confinement that have successfully shown that ASR-induced expansion can be confined through external restraint. Post-tensioning has been done on even a larger scale with the Macroscopic Dam in New Brunswick. Mike Thomas described this in a previous webinar, but this particular dam had some significant cracking, and there was some concern about one potential crack in particular, which may have led to a possible stability issue with the dam. And what was decided here was to apply post-tensioning to the dam by running post-tensioning rod through a cord line here. A face concrete was put on here, reinforced in order to withstand the stresses, and then it was post-tensioned, and essentially this dam was stitched back together. This has actually been done on several other dams, including the Fontana Dam in the United States as well. So again, there's quite a bit of information and data out there in terms of trying to provide some kind of a remedy for ASR in the form of post-tensioning or external restraint. The last example I'll give here will be on looking at relieving stresses. And I'll use the cases here of a dam, but then I'll also segue into some pavement applications. Here's the infamous Macroscopic Dam in New Brunswick. This dam has been suffering ASR for quite a few years, at the tune to about $6 million per year to keep it up and running. The dam has grown about 7 inches vertically during its lifetime. But one of the issues, and Mike Thomas described this earlier, is that this dam actually has integral turbines inside of it, turbines. And what ends up happening here is the concrete can easily expand vertically, but it can't expand in the horizontal direction because of the sides of the dam are confining it. What that leads to is an ovaling of the concrete opening, and it tends to jam those turbines. So what the dam owners have done with the help of contractors is they use a technique known as stress relief. In this case, it's known as slot cutting. And what's done here is, and I'll show it on the next slide, but a diamond wire is literally drawn all the way through the entire dam section, in a small segment of the dam is physically cut out. And the whole idea of that is to relieve the stress and allow the opening, the concrete opening, to be restored back to its spherical and desired shape. This here shows the diamond wire that goes through the dam, and this is actually currently being done on various dams worldwide. You're not alleviating ASR. All you're doing is alleviating the stresses that are caused and hoping to restore some of the operational capabilities to the dam itself. Now, when we look at pavements and other transportation infrastructure, one technique that's often done is when you have a joint like you see here that's significantly deteriorated. What quite a few highway departments have done and continue to do is they will come along here and say remove the outer maybe 1 or 2 foot each side of the joint, and then new concrete is put back in place. And essentially what you're doing here is you're relieving the stress and trying to reduce that deterioration by removing the interfacial region here of the joint itself. Here's an example with alkali carbonate reaction where this curb and gutter section actually expanded so much that it led to the one section of the sidewalk actually riding up on the other. And to relieve that stress, the concrete was removed and a small layer of hot mix was placed just to provide relief at that critical region. So the application of stress relief has been and continues to be done in our transportation infrastructure, and generally we're dealing more with failures at joints and situations like the one I just showed here. So just coming back to these field trials, I just wanted to again let everyone know that these trials are ongoing. Our team is planning one last visit to these sites in the first half of 2013. And the final results will be published by the end of 2013. We're hoping we'll be able to shed some light on these different technologies and determine what methods work best in one situation versus the other. But we just would like to ask for some patience so that the concrete will tell its story in the long run. In addition to the field trials that we've done, I just wanted to spend a couple minutes talking about one other study. And this study is being done at the University of Texas in Austin. And what was done with this study is we cast a variety of different concrete elements that are intended to simulate transportation concrete. The right-hand side here are all reinforced bridge decks, which have a typical detailing, 2 mats of reinforcement. The specimens in the middle here show reinforced concrete columns, which are obviously intended to act as surrogates for large-scale structural columns. And on the far left-hand side, we have unreinforced concrete sections, which are typical of concrete pavements. What we've done is we've triggered ASR in all of this concrete using 2 different reactive aggregates, and at a level of expansion of about 0.1%, various mitigation techniques were then applied to these different elements. They included topical, vacuum, and electrochemical treatment of lithium, the use of coatings and sealants, particularly silanes, the use of FRP wraps on circular columns, the use of overlays, bonded and unbonded, and including Portland cement and hot mix asphalt, and also polymer overlays as well. This study, the study is now complete, and the final report is nearing completion, and this will also be available in 2013 as well. So please keep your eyes out for that. And lastly, in summary, I think probably this first bullet point is the most important point for this entire presentation, that there really are limited options for remediating ASR affected field structures. It's much more efficient and much more intelligent to prevent ASR in the first place, and we really do hope that that the participants of today's webinar were able to participate in earlier ones where the focus was how to test for ASR with regard to aggregates, and how to test for preventive measures, and how to use specifications to prevent ASR in new concrete. In general, what we found is that the methods that reduce the internal relative humidity tended to be the most effective, but again, we know that these type products have limitations. We don't know if they'll be effective with regard to, say, treating a pavement or a abutment where you have water coming from the backside, but we'll hope to gather enough data to answer that question. With regard to the lithium applications, we really didn't see much benefit at all, and very little depth of penetration for topical and vacuum impregnation of lithium. So it doesn't really seem to show much promise in the lab or in the field. The electrochemical method does show potential, and we were able to drive lithium all the way to the surface of the steel, but again, the issue that needs to be considered is the migration of the internal alkalis that tend to move towards the steel once that current is applied. So that's the end of my presentation, and I hope I'll be more than happy to entertain any questions that you might have, and I'll turn things back to Matt. Thank you.
Okay, thank you, Dr. Folliard. We do have some questions, and we are just a bit over our scheduled time, but we will hang on here to answer a few of these before we wrap it up. And I'll also get Dr. Fournier back on the line in case he has any comments on these questions that we'll cover. The first one, has any research been conducted using integral waterproofing agents or water-repelling admixtures to improve resistance to ASR for non-reactive aggregates?
We've done a little bit of work, but it's too early to really determine what the effects are. Most of the work that our group has done as a whole has been more on existing structures and applying some kind of a hydrophobic coating such as silanes. We have done some work where we've mixed integral water repellents into the concrete, but the jury is out right now as to the efficacy of such treatments. I think that the key thing there is whatever technology will reduce the relative humidity below 80% should work well with regard to reducing ASR. And as part of the study with integral water repellents, we are measuring the relative humidity throughout the course of the trial. Okay.
Another question we had was, do the silane treatments have to be renewed every so often?
Well, that's a great question. You know, some of the literature in terms of the manufacturers will recommend some reapplication rate, say every 5 years or so. The experience out of Canada with the Jersey barriers shows that the efficacy has been well over 10 to 15 years now. So I don't think we really have a definitive answer on that at this point. If you have, say, a bridge deck or a pavement and you have vehicular traffic that's applied to it that might abrade away the top layer, we do know that you will have to reapply earlier because you're losing that treated surface. But in the case where you have structural elements that are treated that don't have any abrasive action at all, the only other thing that could really impact the durability of silane would be the UV effects. And we really haven't seen that with the Canadian experience. And I'll let Benoit speak to that because he's been more involved in that in the highway barrier case. But Ben, if you could just speak to how long it's been now and what kind of monitoring has been done and what the long-term results might be.
Yeah, actually, it was interesting to notice, surprisingly, actually, that after about 15 years, we could still see very well the difference between the treated and untreated sections. So I've been since the person who carried out the study retired, and I took over on the study. We're planning actually this spring to have some cores taken and evaluating as well the internal humidity condition in the barrier, because still we can see a fair difference between the barriers, and this information will be published later this year.
And Matt, if I can just add one more point to Benoit's. First of all, thank you, Benoit, for that response. We've done some work with the Texas Highway Department where we developed some recommended practice for the application of silane, and that very question came up again: how often should you reapply? And our recommendation was, I guess, a bit of taking the high road, but we said one should monitor the internal relative humidity, and if that relative humidity begins to rise with time, then we can consider that the silane's efficacy is beginning to wear off, and you should consider another treatment. So that would be one way that you could determine whether or not you need to reapply it, is just by measuring the relative humidity of that section compared to a control.
Okay, excellent. The next question is, what technique did you use to quantify lithium?
What we did is, in terms of the profiling, we would take cores from the field back to the lab. Then we would surface grind the concrete 1 millimeter at a time, the same way that people would typically use for determining chloride diffusion. And then once we had the lithium from that, we then extracted the lithium and tested it in with the flame photometer test to measure the lithium concentration. And we've done that at our different laboratories, and we've done some round-robin testing to ensure that we're all getting comparable values in terms of lithium concentrations. And the technique seems to be quite effective.
Okay, the next question is, what is the application rate of the silane? And again, along with the question previous, how often is treatment required?
Generally speaking, and you know, I should say this first, every product has its own recommendation, and we would always refer to the recommendations from the supplier. But our experience is it's typically 1 gallon for every 125 to 150 square feet. That tends to be pretty consistent across most of the silanes that we've looked at. And again, I guess we already referred to the issue or discussed the issue on reapplication. But I would say, first of all, refer to the manufacturer's recommendation. But our experience has been somewhere in that range of 1 gallon per 125 to 150 square feet.
Okay, very good. The next question is in regards to slide number 23. The attendee asks, how old was the barrier when the first time lithium treatment was applied to it?
Okay. I'll go back to that slide real quick here. And this more than likely will be a question for Benoit if it's the Canadian experience. Mm-hmm. So let me first mention the Boston case, because I actually mentioned 2 separate ones. So the Boston barriers, Ben, I think these were about 10 years old to 12 years old when we treated them.
I think so, yeah.
If I recall correctly. And then with regard to the Canadian experience, I was not involved in that, so I'll ask Ben if he could.
They were about 15 years old. Yeah, those. Yeah.
So I guess both sets in Canada and the U.S. were both in the range of 10 to 15 years in age prior to treatment.
Okay, thank you. Next question is, which treatment works better for pop-outs?
Huh. I don't think we have a definitive answer for that. I think anything that can reduce the tendency for ASR will reduce the tendency for pop-outs if that specific aggregate is prone to pop-outs. So, certainly a silane treatment where you can reduce the internal relative humidity. By stopping ASR, you will reduce the tendency for pop-outs, especially of chert particles. We haven't been successful enough in terms of driving lithium in to pavements that would typically have pop-outs, so couldn't really tell you whether lithium could be effective in that regard. It's all a matter of finding a way to get it into the concrete. I don't know if, Ben, have you had any experience specifically with pop-out treatments?
No, not more than what you have described.
Yeah, so we in all of our field trials, pop-outs were not really a main issue, but we have seen in other, especially pavements, issues where pop-outs, and also seen them in residential environments as well, around swimming pools, etc. So, certainly applying silane, trying to dry the concrete out, try to improve drainage away from the pop-out region, all of those could potentially help, but that's about all we could offer at this point.
Okay, very good. The next question is, are there any safety issues with handling lithium?
Not with lithium nitrate. Lithium nitrate is much safer than its predecessor, which was lithium hydroxide. It's been applied in various states and has been able to meet the regulations for those states. We use typical protective gear in terms of eyeglasses and gloves, say. And it's never really been a major issue with regard to potential runoff from a pavement surface. It's my understanding lithium nitrate is much more friendly environmentally in terms of its impact. So it doesn't seem to be an issue at all with anything we've seen.
Okay, the next question is in regards to slide 33, and the attendee is asking if you could explain again how the lithium blocks expand more than the control ones. Yeah,
it's a good question. To be honest with you, we're not quite sure why, but the only explanation that we could really come up with was that it was just given the fact that this particular block here, this is the one that was ponded for 8 months, moisture is a driving force for ASR, as we know, and that's why we try to dry concrete out. And what we suggest might be the case here is that if you pond it continuously and you're applying both water and lithium, it's just possible that you're increasing the saturation of the concrete, which may make expansion worse. It's conjecture. We don't have data to support that, and it's just based on discussions we've had within our group. Also, what should be mentioned is that these are large concrete blocks, and the data I showed was for the average expansion of the block, but we've also looked just for the expansion of the top surface of the concrete, and again, we don't see any reduction when lithium is applied long term, and in most cases, we actually do see that increase.
Okay, next, this is a three-part question. What was the long-term performance of the externally restrained concrete? Is the process not capable of inducing stresses that can cause local damage? And if the structure is a column, is it not already restrained?
Oh, good questions. Well, with regard to, let me take the third part of that first. If the column, certainly a column itself is restrained internally through the reinforcement, and oftentimes that internal reinforcement is enough to confine the ASR that's within that caged region itself. But there will be cases where the expansion may exceed the capacity or the elasticity of that steel, or where the concrete beyond the reinforced region, the covercrete, is cracking so considerably that the concern now becomes chloride or water going through the cracks and reaching the steel. So the idea would be to provide additional external restraint that would envelop the entire structure and thereby protect it from the elements, and also provide the external restraint. I'm not sure about the case studies in terms of the long-term results, other than the data that was shown in the presentation today. And there doesn't seem to be any negative effects structurally from it. But again, we're all materials folks that are involved in this project, and we always strongly recommend bringing in a structural engineer when you're considering any kind of an external application of restraint. In our own exposure site, we do have different, just to address that one point, we do have some columns that we have applied some FRP wraps to, and within those columns we estimated how many layers of FRP wrap we might need to restrain ASR, and we then applied different amounts of that to see if we could actually capture that effect. So, for instance, I think we estimated that 1 to 2 layers of FRP wrap would be enough external confinement, and we did a study where we did 1, 2, and 4. So our hope and our thinking is that the least confined one should actually fail, which we would then observe, and the one that has the most layers of FRP wrap should provide enough external restraint to basically take care of the ASR. So, but that's a very good question. Thanks.
Okay, and the next one is ASR improved by use of high-performance concrete? A
higher performance concrete will do better with regard to ASR, but it will not be resistant to ASR. What we've seen is it often will delay ASR because of the lower permeability, but ultimately, if the alkali loading inside the concrete is high enough, you still will get ASR. It might just be delayed for some period of time, but it certainly is not. It certainly isn't the answer by itself. Now, if that high-performance concrete included sufficient amounts of fly ash, slag, or silica fume, so that that you're actually reducing the pH internally enough, then the HPC would be the answer for ASR. But let's say you had another high-performance concrete mix that in and of itself was not resistant to ASR. That concrete would last longer, but it eventually would fail as well.
Okay, very good. The next question, does the age of the concrete affect the performance of the lithium treatment? And do you have any research that would suggest which way to apply lithium is better to prevent the ASR? For example, adding the lithium when mixing the concrete or applying it to a mature concrete like the cases in your slides?
Okay, it's a good question. So we've done, our group and many researchers have worked with lithium as an admixture, and it's very effective if you put enough lithium in to concrete, and it can provide long-term resistance to ASR-induced expansion and cracking. So the best case for using lithium is to use it as an admixture. Just make sure that you put enough in for that given aggregate type. Generally, that requires laboratory testing to determine how much is needed. But the data from our exposure site, as well as sites in Canada and the UK, show that lithium is a long-term solution for ASR when enough lithium is put in. The challenge with field structures isn't so much the age of the structure, but it's the ability to get the lithium into the structure. And our experience has not been very favorable with regard to getting sufficient depths of penetration of lithium, with the exception of the electrochemical technique, which I described. But lithium as itself is a very viable technology for controlling ASR, generally much more suitable for new concrete as opposed to existing.
One of the critical factor also that I don't think has been evaluated to a good extent at this time is that when we were testing lithium admixtures for preventing ASR, we found that the response to lithium admixture was very much different from one aggregate to another. So and as Mike Thomas was presenting last week, we found that in many cases, the aggregates that were found to be responding the best to lithium were those that were the most reactive aggregate material. And so one question that may arise from that kind of experience is that if you were able to drive in lithium in the concrete, as Kevin explained, would the amount of lithium that you drove in the concrete be enough with the particular aggregate that you have in the concrete? That also will vary quite a lot from one aggregate to another that is incorporated in the concrete. So it means that we may be able to drive lithium in, but that may not be enough with the type of aggregate that you have. So this, I don't think, has been, has been evaluated to enough extent at this stage.
Okay, we're going to go about 10 minutes more, and we have a few questions left, so we'll roll right along. When was the repair done at the Quebec transmission tower footings? Year and date, please.
Ben, would you know the specific, any question related to Canada? I will kindly pass off to Benoit.
The time and date per se, that's a good question. It is, oh boy, I would say it's probably, the paper that we see on that slide, that figure is from a paper from Jurin 2000. And I believe that the treatment was done probably between 5 and 10 years before that. So the treatment would probably have been done in the early 1990s, from what I can recall. But I could check and make sure that I can give you the right answer on that. But that's my that's from what I can recall right now.
Okay, fair enough. The next question is, does cutting slots through a water retaining structure such as a dam lead to leaks?
Well, certainly it might, but the experience with these dams is by the time you actually pull that wire all the way through the dam itself, there's so much stress that's still built up, it will actually close right behind it. In fact, the early trials had a lot of issues with getting the diamond wire actually stuck during the cutting process itself. So I think because of that effect, there's so much built-up strain and stress in that dam that it eventually, or in fact almost instantaneously, will close behind it. And as we mentioned before, about 1.5 feet have already been taken out through that slot cutting process, and I don't think that there's been any inherent major issues with regard to increased leakage.
Okay, the next question is, what is the practicality of electrochemical method on large bridge structures?
Well, that's a good question. Well, it is a very resource-intensive and expensive treatment. So the practicality all comes down to how important the structure is and what kind of benefits one's expecting from it. The challenge is that we had 2 columns treated as part of our study in the Texas, with regard to the Texas columns, and it's very difficult to take the cost of the treatment that for a small experimental section and apply it to an actual repair job, because most of the cost is actually the setup itself and the logistical aspects of it. I guess the better question, or perhaps a parallel question, might be is, before considering that, we just need to kind of close the loop on the issue of the buildup of the alkalis at the surface of the steel, the internal sodium and potassium. And I think once that's sorted out, that will determine whether or not the electrochemical approach is viable. And then it all comes down to economics for the owner. The potential benefit, the potential increase in service life relative to the cost of the treatment itself. So we don't really have a definitive answer for you there, but just some general thoughts.
Okay, well enough. And the next question is, what is the best method to check a concrete that is suspected to have a reactive aggregate but does not show any external signs of ASR?
Yeah, I'll defer that one to Ben, because I think it's going to fall in the hands of a petrographer.
Yeah, this is very much the case, Kevin. I would say that probably the best thing to do is to grab a core, do a petrographic examination. To complement that, some expansion tests can be done on the cores to determine if there is any potential for expansion. One test that we've been also doing that is qualitative, but it is a very interesting tool for determining potential reactivity, is to do what we call a gel pat test. So if you have if you take a concrete core, you slice it in half, you polish the surface, you can immerse the core in a 1 normal NaOH solution at 38 degrees C, and then with time you can just take out the polished section from the solution and look at the surface, and you will see gel developing at the surface of the reactive aggregate particles. We have done that on a fair number of cores from different concrete structure, and actually it is a powerful test that can give you an idea whether or not the aggregate is potentially reactive. It's not quantitative, but in terms of just showing if there's a potential for ASR, that works quite well. Just as a compliment, while Kevin was answering some questions, I checked for the steel towers in Quebec. They were built in the mid-60s, and the repairs were done actually in the late 1980s. So the monitoring started at about I think it was 1992, and the data that you see in the paper that Kevin showed was in a paper of 2000. So that was about 8 years of monitoring after the structure had been repaired.
Okay, thank you for those additional details. We're going to go ahead and wrap it up now. We got a couple questions left, but we'll try to respond to those directly via email after the webinar is over. Just want to say again thank you to our presenters. They did an excellent job. Dr. Thomas, Dr. Fournier, and Dr. Folliard. Thank you also to the attendees. We've already gotten some really good feedback, and we appreciate that. Again, we hope it was beneficial for you. We appreciate all the many good questions that we received. And just watch your email inbox for some information regarding downloadable PDF versions of all the presentations. And remember that if you missed any portion of these webinars, they will be posted online after the final face-to-face workshops are completed in May of this year. So thanks again for attending. Have a great day.
Thank you.
Thank you.